Hey guys, this is Statistical Applications. This is going to be our new unit. Today we're going to be looking at the normal distribution and the percents of those curves. Normal distribution is just a more sophisticated way of displaying data, and we can also use it to predict future data. Important things about a normal distribution, the reason why we like it so much is because it's symmetrical. And symmetry means that I can find different patterns, okay? Another thing to know about the normal distribution is that everything under this curve is considered 100%, right? It's 100% of the data is underneath this curve. Some of the variables that we'll be using the two variables that we'll be using is mu, and that is for our mean, or the average, however you want to say that. And then sigma is the standard deviation. I know you guys talked about standard deviation at the beginning of last year. We're bringing it back. It's going to be new school, okay? So, the normal distribution has a nice bell shape. You're going to have to use your imagination with my drawings. I apologize. So, notice that there's no y-axis over here. Right? We don't care about the y-axis. We care about this x-axis. And on the x-axis, when you're making a normal distribution, the first thing you're going to plot is your mean. Because if you notice, all of these next values are all based off of the mean. Okay? So we plot our mean, and then you use the standard deviation to get to the next point. And then you use 2 standard deviations to get to the next 2 points. And then you use 3 standard deviations to get to the next 2 points. Now, something that's, remember how I said 100% of our data falls under this curve? Well, that's because and also that it was symmetrical, right? Well, this helps us play into some things, right? So, between these first 2 standard deviations, there are 68% of our data falls in here. Okay? So that means if I just wanted to find this right here, it would be 34%. Right here would be 34%. Right? So this is the nice thing that happens when you have a distribution that's symmetrical and a standard deviation. You can figure out how much falls in between these 2 points. And then in between the second and the 2 second standard deviations, you have 95% of your data falls in this area. And then lastly, not lastly actually, you have one more, but here you have 99% of your data. And then on the outskirts, you have 100% of your data. So that means 1% falls here and here combined. Okay? So, let's do an example. I know it looks kind of complicated, and I think a lot of that's just because there's these Greek letters that you're not really used to, but it's not that complicated. So, let's do an example. So the waiting time for an elevator is normally distributed with a mean of 1.5 minutes and a standard deviation of 20 seconds. Sketch a normal distribution diagram within 3 standard deviations of the mean. So first thing I'm going to do is I'm going to make a x-axis, and I'm going to label it. It's going to be in seconds. And I'm going to plot my my mean. Now, my mean is in minutes. I don't want that. I just labeled my x-axis as seconds. So, what is 1.5 minutes in seconds? It is 90 seconds. So, let's plot that, and it goes right in the middle. And I call it 90 seconds. And now, I'm going to make 3 units on either side of that. That's kind of right. kind of even, but we're going to go with it for the sake of time. So the standard deviation is 20 seconds. So that means that each time I go up 20 seconds. So it's going to be 110, 130, and 150. Over here, same thing, 70, 50, and then 30, because you're going down, right? Now, I'm really bad at doing this on the iPad and on the board, so bad in general. But I'm going to make these points, and they need to be kind of symmetrical, right? Because our bell curve is symmetrical. And then as you get further away from the mean, your points need to get closer and closer to the x-axis. Because remember, from one standard deviation, 68% of that, so the majority of your area should be within one standard deviation of the mean. And then within 2 standard deviations of the mean, you get smaller. And then within 3 standard deviations of the mean, you should get really close to your graph. Okay, this gives us a nice bell-shaped curve. So now I'm going to connect the dots nicely. Oh, this is better than the last one. Okay, good. Okay, so this is the normal distribution diagram within 3 standard deviations of the mean. Okay, now we are going to move on to the next part. And it says, find the probability that a person waits longer than 2 minutes and 10 seconds for the elevator. Well, I'm going to bring back that nice little bell curve. All right, now, first let's find 130 seconds. It's right here. And it's on the second standard deviation above the mean, right? So, I know that from here to here is 95% of the data, okay? I do not care about this data. I want to know 130 seconds more, right? So I can get rid of this 95%. But what am I going to get rid of out of? Well, I want to know all of this up here, right? So I'm going to take away 95% from 100%. So 100% minus 95% is going to give us 5% left over, right? But the thing is that 5% is from 130 and everything lower than 50. So it's both of these combined. This is where the fact that the normal distribution is symmetrical comes in handy. So all I have to do is take 5% and divide it by 2 in order to get the percent that will wait longer than 130 seconds, right? So I take 5% and I divide by 2. I'm going to get 2.5%. So find the probability that a person waits longer than 2 minutes and 10 seconds for the elevator. That probability is 2.5%. See, it's not too bad, right? It's okay. Let's do another one. Find the probability that a person waits less than 1 minute and 10 seconds. Again, bring back that nice little bell-shaped curve that I worked so hard on. And I'm going to convert this minutes and seconds into just seconds. So I get 70 seconds. I find that, and you should always, I shouldn't say always, but when you're doing it without a calculator, you can only do this with, can't say only, but it makes it nicer to only use the standard deviations points. So less than 70 seconds. Again, you want to look at the overall curve, and in between 70 and 110, you have 68, that was bad, 68%, right? So let's subtract that from 100, and you're going to get 32. So 32 is from here this way and from here this way. But we don't care about what happens over here. We only care about here. This is what makes us happy, is this place over here, right? So, what are we going to do? We're going to take 32% and divide by 2. So 16% is our answer for this problem. One more time, guys. So, calculate the number of people expected to wait less than 50 seconds for an elevator. What do you think we're going to do? Bring it back, right? We're going to bring back our nice bell-shaped curve. Look for 50 seconds. It's 2 standard deviations below the mean. And I'm going to first find that percent, right? So I know that from 50 to 130 is 99%. And when I make this line, I'm just trying to don't worry about that line. Anyway, so 99% falls in between 50 and 130 seconds, right? Or 95, sorry. Guys, you gotta tell me. I messed up. Oh, that's right. We're on a video. Anyway, so 95% falls in between these standard deviations, right? So, again, I don't care what happens up here. I care about what happens down here. This makes me happy. So, I'm going to take 100 minus 95. I get 5. I divide it by 2 to get only half of that information. So, I get 2.5%, right? Now, I want to know what that is of 200. So if I take 200, because that's how many people, right? I'm trying to predict what happens. Calculate the number of people. Oh crap, I forgot to tell you. Yeah, sorry. So there's another part up here. If 200 people are waiting in line. I apologize. So 200. So I take 200 and I'm going to multiply by 2.5%, but I can't do that because it's percent, so I need to change it into a fraction form, or into decimal form, and I do that by making this come out twice, so it's 0.025, so I multiply 200 by 0.025, and I get 5 people. We should expect 5 people to wait less than 50 seconds for an elevator. Whew, guys, we made it. Awesome job. I'll see you in the morning.